Okay, so spin echo, and this is actually a consequence of using 2 RF pulses. Erwin Hahn observed this in the early 50s, that when using 2 RF pulses, then there is an echo observed at twice the time difference, and this happens in the presence of a constant gradient. You might ask, well, in the 1950s they did not have gradients, how come this was observed? Well, actually at the time, the quality of the magnets as they were used was so poor that they actually were like the B0 was really not static, it was not constant, was not homogeneous, so there was a big gradient inside the magnet. So we'll look here at time. We'll now pretend that we've turned on the gradient along y and this is always on. So we'll just consider it is always on. We'll have a 90-degree pulse. This 90-degree pulse, the B1, is applied along the x-axis, so it rotates the magnetization onto the y-axis. After a certain time, we will apply a gradient, an RF pulse of twice the duration, so it's a 180-degree pulse, but this time around the y-axis. This time here, we will call this TE half, and we're going to look at what's happening after another time TE half. And at this point, actually, we will observe a spin echo. So I'll take here the graphic, what happens with the magnetization. We're at after the 90-degree pulse, we have the magnetization flipped into the transverse plane. It's along y. So it's a 90-degree pulse along x. The magnetization is all in phase along y. And now we're going to look at what's happening over time. And we're going to look at the magnetization vector in complex space. So the x magnetization component is, for example, imaginary, and the y is real. It doesn't really matter what we're using here. So we have magnetization here, and I'll just draw 4 random magnetizations. They have different Larmor frequencies and or different signs of the Larmor frequency, all in, of course, the rotating reference frame. So after the 90-degree pulse, all the magnetization is collinear, and now what happens during the time period is dephasing. We'll have 2 vectors going to the left and 2 vectors going to the right, and this is what's happening during the first TE half. So it's dephasing, depending on their position along y, depending on they will precess positive or negative and with different Larmor frequencies. So after TE half, we have these 4 magnetization vectors that are spread out. So this is the situation B that we have here just before the 180-degree pulse. They have spread out between fast and slow. And now what we are going to do is we are going to apply the 180-degree pulse along y. So we're going to apply the RF pulse along the y-axis. What does this do? Did you see? Let's do it again. It flips the x component of the magnetization. An RF pulse that rotates around the y-axis will leave the y component intact. We'll go back. So this is before the pulse. And now, after the pulse, the x component has changed the sign for the vectors. So, orange and blue on the right, red and green on the left, and now red and green are on the right, and orange and blue on the left. The y components are the same, but the x components have changed the sign. So this is the situation here just after the RF pulse now. So if we look at, now I just want to look at what happens with the RF pulse. We only change the x component, the sign, so we have transverse magnetization at a certain position for any of the 4 magnetization. We only change the x component, so the x component changes sign. So now the phase. And the phase can be the effect of the gradient here, so it's gamma gy y TE over 2. So this is the duration times the gradient times gamma times the position. That gives us the total phase. And now what we are going to do, we're going to look what happens from now on. And we remember blue and orange move faster in this direction, red and green move in this direction. So if I go back, red and green moved in this direction, blue and orange moved in this direction. So we're going to redo this because they are going to keep their precessional orientation and speed. And as we do that, going from C to D, they continue to go with the same precessional frequency, but in the end, all the magnetization vectors will align themselves and be collinear again, and hence form an echo. And this is called a spin echo. So if we look at this in complex terms, so we have the transverse magnetization, we have this phase before the 180 degree, so the influence of the inhomogeneity is here before the 180 degree. The 180 degree, from this expression, we can also write the transverse magnetization complex as m transverse times e to the I minus I phi. So it basically pretends as if the RF pulse does as if the inhomogeneity that has been applied is switching its sign here. This is, if you want to make a link to the gradient echo that we've discussed last week and this week, then the 180 degree pulse in this scheme here acts as if all the inhomogeneities that are static here are changing their sign in here. Of course, they're not doing it, but we can, to understand how this echo is done, from this expression here, we can pretend as if this was happening. So it's a Gedanken experiment. So this, in terms of phase evolution, it's as if this static gradient was with the 180 degree, was flipping its sign. Okay, so I want to revisit the spin echo formation. We had a graphical argument why we have echo formation with a 90-180 degree pulse, and I want to take here a more mathematical approach. So we'll have the RF field, we'll do a flip angle alpha. We have a gradient along x, and we'll look at the time point 1. At the time point 1, we just have z magnetization, so this is our magnetization vector. Then we rotate it by alpha degrees. So at this time point 2, we have the magnetization is mz sine alpha and mz cosine alpha. And now we'll just consider the transverse components, so 0 and my. We just have my magnetization because we're not concerned with the effect of the flip angle here. And now we'll look at just the magnetization in the transverse plane, which precesses now with a magnetic field that's given by gamma gx times x. So here's our gradient, gx. We have the echo time Te. We'll look at time number 3. So at time number 3, we have now a precession of the magnetization. So the x component increases with cosine, the y component with sine, or vice versa. And so we have expressed it here that the my component is given by the cosine of phi x and sine phi x. Now the 180 degree pulse inverts the y component of the magnetization, so my becomes minus my at this point. And so we can now write this as my times cosine phi x minus sine phi x, or my cosine phi cosine minus phi x and sine minus phi x. So this is essentially identical to the effect of a negative gradient, like we have argued last week, and therefore it produces an echo. So the signal decays, and in general one considers that the signal decays exponentially due to T2 or T2 star relaxation. And what is the link between the two? So if we have the transverse magnetization here, then we have T2, that's the decay with T2, and the decay with T2 star with a gradient echo is faster. T2 star is always shorter than T2. So if we use gradient echo for refocusing, we have T2 star effects. If we use spin echo, 90 degrees, 180 degrees, then we have the T2 effect. The two are always linked due to the imperfect magnetic field in a given voxel. This term is never exactly 0, and this is unavoidable in practice, since magnetic field in a object of finite dimensions and complex anatomy like we are, the B0 that is in the body is never perfectly homogeneous. However, this unavoidable effect is also exploited in bold fMRI like we have just discussed. So now we come to the next imaging sequence, and the last one that I want to introduce here in terms of spin physics, that's the spin echo sequence. So we have RF excitation of the slice. So this is just like we have had for the gradient echo. we have had the dephasing of the gradient, the rephasing of the gradient. Now we have the 180-degree pulse, and here the gradient is just placed symmetrically around the 180-degree pulse, as we have seen in the previous two slides. Symmetric placement of a static gradient will produce no dephasing of the magnetization around the 180-degree pulse. For the frequency encode gradient, which here in this example we'll presume it's along x, we have the dephaser. It's now before the 180-degree pulse, so now the dephaser has the same amplitude or the same sign as the frequency encode gradient. Unlike the gradient echo where it was negative beforehand, this is now positive in the same direction as the frequency encode gradient. That has again to do with the fact that we have the 180-degree pulse in between. So this area and the placement of the 180-degree pulses together, that defines the echo time TE for this sequence. We have then the signal, the echo that is being recorded, and finally we have the phase encode gradient along y in this particular example, applied for example here, which induces the phase encoding for the second dimension. This is of course applied every TR seconds, and so this is what the spin echo sequence looks like. So very similar to the gradient echo. The fact that the 180-degree pulse is here changes the sign of the readout gradient, and the signal is now influenced by T2 and not T2 star. So if we look now at the signal, and the signal is proportional to the transverse magnetization. For proton density rho, this is proportional to the equilibrium magnetization. Now we'll just consider 90-degree pulses here, so the transverse magnetization at this point is equals to the Z magnetization just before the RF pulse times sine of 90 degree. At the time TE, the magnetization, transverse magnetization is given by the transverse magnetization here times e to the minus TE over T2. And the Z magnetization just before the pulse, which is the last parameter that we need to understand here, is 1 minus e to the minus TR over T1 times M0. Those are the longitudinal coherence parameters for 90-degree pulse excitation, and you can look that up in lecture 9 and 10 when we dealt with this situation. So this is for this 90-180-degree sequence is the signal behavior. So as we repeat this every TR seconds, we want to acquire an image. We have to repeat it every TR second, produce a 2D image. So our signal now becomes a function of the experimental parameter TE, TR. It is proportional to the proton density, M0, times e to the minus this term here, that's longitudinal coherence, and this is the decay of the signal due to T2 for the spin echo sequence. And we'll work now through the basic contrasts. How do we take from this equation here, which has a number of terms, how do we produce the three basic contrasts, proton density, T1 weighted imaging, and T2 weighted imaging, that I introduced at the beginning?